Something strange might be happening with Comet 3 AI. Reports suggest NASA instruments could have detected sudden repeat events from this interstellar visitor. If these observations are real, they could show multi-wavelength activity spikes across different types of radiation. What if these aren't random flares? What if there's a pattern here that could reveal something profound about how interstellar comets behave when they encounter our sun's influence? We're going to explore what scientists call a burst fingerprint, examining how such events might appear across infrared, ultraviolet, X-ray, and radio wavelengths. Different instruments would see different things, and that combination could tell us exactly what's causing these potential outbursts. Could solar weather be triggering these events? When our sun hurls charged particles and magnetic fields into space, what happens when they slam into a comet that's been drifting in the cold of interstellar space for billions of years? We'll test whether any repeating pattern might match a rotating lighthouse model. Imagine jets of gas and dust sweeping past us as the comet spins, creating regular pulses of activity. Everything we discuss stays grounded in real physics. No wild claims, no science fiction, just the genuine mystery of what happens when an ancient wanderer from another star system gets heated by our sun for possibly the first time in eons. If there's truly a fingerprint in the data, it points to a physical cause we can understand and test. The question is, what story will that fingerprint tell us? If these reported bursts are real, they wouldn't just show up as simple changes. True cometary outbursts create signatures across the entire electromagnetic spectrum. And that's where things get interesting. If you love this no-nonsense approach to space mysteries, tap subscribe. It genuinely helps support content like this. Think of it like a cosmic crime scene. Each wavelength of light tells a different part of the story. In infrared, we'd expect to see carbon dioxide absorption lines suddenly brighten. When trapped CO2 ice vents rapidly from deep within the comet, it absorbs specific infrared wavelengths. The James Webb Space Telescope would be perfect for catching this. It's designed to spot exactly these kinds of molecular signatures. Switch to optical light, and you'd see cyanogen emission lines spike upward. When fresh molecules get blasted out of the nucleus and hit sunlight, they break apart and glow with that characteristic green color we sometimes see in comet tails. Ground-based telescopes like Gemini or the Very Large Telescope could track these changes in real time. Ultraviolet tells another story. Solar UV radiation drives intense photochemistry during outbursts, breaking apart water and organic molecules. The Hubble Space Telescope's UV capabilities would reveal this molecular destruction happening live. Here's where it gets really intriguing. X-rays. When solar wind particles slam into neutral gas from a comet, they swap electrons in a process called charge exchange. This creates X-ray emission that space-based observatories like SWIFT can detect. Charge exchange X-rays happen when solar wind ions grab electrons from cometary gas, releasing energy as X-rays. Finally, radio telescopes might catch the 18-centimeter OH line getting stronger. This is the radio signature of hydroxyl molecules, essentially broken water. When sunlight splits apart water vapor, it creates OH radicals that emit at this specific radio frequency. The 18-centimeter line serves as a radio signpost, showing us where water is being destroyed. A coherent fingerprint across all these bands wouldn't be random. It would point to a real physical mechanism driving the outburst. Different processes create different patterns, so the combination acts like a diagnostic tool. Here's the big idea. If bursts are happening, they leave footprints across the electromagnetic spectrum. When infrared, optical, X-ray, and radio signatures jump together in a coordinated way, that's not coincidence. That's the comet breathing, releasing stored energy in a way we can measure and understand. We can test this hypothesis like detectives, checking each wavelength band by band, spectral line by line. The beauty is that different instruments would see different pieces of the puzzle, and together they'd tell us exactly what's happening inside this ancient visitor from another star. If the fingerprint timing matches up with solar activity patterns, we'd have our smoking gun for what's triggering these potential events. Solar weather as the hidden switch. What if the key to understanding these potential bursts isn't the comet itself, but what's happening with our sun? Scientists could cross-reference any burst timings with data from the ACE and DS-COVA spacecraft, which monitor solar wind conditions in real time. These satellites sit between Earth and the sun, giving us advanced warning when coronal mass ejections or high-speed solar wind streams are heading our way. If a comet burst, followed the arrival of a CME by a few hours or days, that would be a clean physical trigger we could test and verify. The mechanism is straightforward. When more charged particles from solar storms hit the comet's coma, they dump extra energy into the gas and dust cloud through collisions and electromagnetic interactions. Think about it this way. 3AI has been drifting through the near vacuum of interstellar space for potentially billions of years. Its surface and any exposed ices have never experienced the intense charged particle environment around an active star. When our sun's weather suddenly intensifies and slams into this ancient visitor, the comet could respond in ways we've never seen before. Solar storms turning a comet on and off like a cosmic light switch. That would be remarkable evidence of how dynamic the space environment really is. But what if the pattern wasn't just tied to solar activity? What if there was something even more clockwork about these potential events? This is where the rotation lighthouse model comes in. If multiple bursts occurred at regular intervals, that might point to something rotation-locked, meaning the events are tied directly to how the comet spins. Picture a rotating lawn sprinkler. Each time the water jet sweeps past your position, you get soaked. Then there's a gap until the next rotation brings the jet around again. A comet with active vents on its surface would work the same way. As 3AI Atlas rotates, different areas of its nucleus face the sun. If certain spots contain more volatile ices or have structural weaknesses, they could release jets of gas and dust when solar heating hits them at the right angle. From our perspective on Earth, we'd see these jets sweep past us once per rotation period. By measuring the time between potential bursts, astronomers could infer the comet's rotation period. Maybe it spins once every 12 hours or 3 days or some other interval we haven't pinned down yet. The real test would be checking if the multi-wavelength fingerprint we discussed earlier repeats in phase with this timing. If the infrared CO2 spike, the optical cyanogen glow, and the radio line all strengthened together at regular intervals, that would strongly suggest jets anchored to stable surface vents, rotating with the nucleus. Rotation locked means these aren't random events. They're tied to the comet's spin, predictable and measurable, and here's the crucial follow-up question. If jets are pushing material away from the comet in preferential directions as it rotates, that should create a tiny rocket effect. The comet's orbit should drift slightly from pure gravitational motion, leaving traces we could detect in its trajectory. If these bursts are real and tied to rotating jets, they should leave a signature in 3AI's trajectory itself. Astronomers track this using what are called A1, A2, and A3 parameters. These mathematical terms capture how jet thrust pushes objects in 3 different directions: radially away from the sun, perpendicular to that in the orbital plane, and perpendicular to the orbital plane itself.